Hello and welcome to my video, lesson 2.5 on charged droplets in fields, in electric fields. So, if you haven't yet watched my electric fields video, and especially the parallel plates video, then please go back and do that, because it won't make sense without that. So, we're going to look at Millikan's oil drop experiment first, to talk about what he did, because what he did is he found the elementary charge of an electron that we now know to be 1.6 times 10 to the negative 19 coulombs. He figured this out. He was the first one to figure this one out. And it's a pretty cool experiment, honestly. It's painful to do, physically painful, because you have to bend over the whole time and kind of stare through this hole and your eyes are drying out while you're looking at stars. But it is a cool experiment. So let's investigate. So essentially, this is the experiment. Over here, he has an atomizer, which is essentially just a method of making the particles really, really small. Sort of like a perfume bottle, how it sprays it into very fine mist. This is an atomizer. It makes things small, really small oil droplets. Not to the point where you're getting one electron at a time or you're even 10 electrons at a time, but where you're getting hundreds of atoms at a time. And so what happens is he shoots a whole bunch of particles up here. Now, they're going to just start to fall naturally. That's just what happens. You know, gravity. It's wonderful. And so as they fall, some of those will happen to be positively charged, and some will happen to be negatively charged, and some will happen to be neutral, or at least close to neutral. So what we're going to do is we're going to make this plate, I'm going to make it red, I'm going to make this plate negatively charged, okay? Because most commonly what we're looking for is those positively charged particles, oil drops, okay? And what happens is we're going to have this oil drop in here that's positively charged, and it's going to be sucked upwards by the negatively charged plate and pushed upwards by the bottom positive plate. And by doing this, we're going to end up with a net electric force up. Now, because it's a particle with real mass, it also has a force of gravity down. So now it has the force electric up and a force of gravity down. And so what you can do is you can vary the voltage here across these plates. You can change the voltage. You can change the voltage here and make these two things balance. Okay. Now, once they are balanced, so it's like this. It's F net equals ma. And how do you know they're balanced? Well, they're balanced when the particle is no longer accelerating. Right? It could be moving at constant velocity, but worse, just it's stationary at rest. But the idea is that the acceleration is zero, or at least close enough to zero that you're able to calculate this portion, and you can essentially get rid of it. So you can watch the particle drop and use kinematics formulas to solve for the acceleration if you want. But essentially, we'll pretend like that turned into zero. So when that turns into zero, we can then move gravity over. The force of gravity now equals our electric force. Now, this is a wonderful realization because we know that our mass times gravity is going to be our, times 9.81, is going to be our force of gravity down. And if we look at our formula sheet, we can also see that we have an electric force given by this formula, so Q and then E. Okay, Q is the charge of the actual particle, and E is the electric field. Now, this is fine, but we don't know the electric field quite yet. How can we get that electric field? Well, again, another formula. because we know the voltage change and we know the separation distance of the plate, which is just the literal physical distance between here and here. Okay, so the separation distance as well as the voltage, we're able to, let me go back at the formula there because I don't want to mess that up. It's delta V over delta D, so just V over D. Okay, so in the actual apparatus, when it's built, you make sure you get a very good D value. You're able to vary the voltage, change the voltage on a modulator beside, so you're able to know what the voltage is, and we know 9.81. But, so with all of this said, let's do one more little switcheroo. We're going to have mass over Q equals, and then we're going to have V over dg. And so what this is saying is we know this side completely, so now we're solving for this ratio, the charge to mass ratio of the particle itself. Okay, and so when you do that, you can also figure out the mass basically by just comparing it. What if you change the voltage the other way? So you can vary this. You can vary this voltage, and you can change this electric field here. And by changing that, you can essentially, rearrange this equation to solve for your m. So it's essentially that. Okay. So basically, at the end of all this, Millikan finds out a bunch of different answers for charges. Now, these charges are not, one electron. Okay. 1 electron is 1.6 times 10 to the negative 19. That's 1 electron, okay? But what he ends up finding is a bunch of other charges. So this is a simplification, but essentially he finds a bunch of other charges: 3.20, 4.80, 3.20, another 4.8. Another 4.8, maybe a 6.4, and maybe another 6.4. And what he sees here is when he bunches this up, he can see that there's always certain gaps that occur. Okay, basically, if he graphs this, it's really quite cool. He graphs it. He's going to find a bunch of charges at one certain energy level. Okay, and then we're going to find another bunch of charges at another energy level. And we're going to find another one at another energy level. And essentially what he's doing is he's looking at, well, what's the change? What's the difference between these two? What's the difference between these two? What's the difference between these two? So taking an average of all of these, he gets 3.2 here and 4.8 here. So what's the difference? 1.6. And then 4.8 to 6.4, what's the difference? 1.6. And then maybe 8.0, what's the difference? 1.6. So he's looking for this difference between the different levels, the different charges. And even though he can't measure 1 electron at a time, because he's finding these differences, he's able to figure out what 1 electron actually looks like. It's quite a cool experiment. Truly it is. So that's essentially the idea of Millikan's oil drop, and he found it to 1% from my Googling, 1% of the actual, modern day answer. So quite well done from Millikan. So anyways, let's take a look at a couple example questions that are kind of related to this. Find the magnitude of a charge on that oil droplet with that mass if it's accelerating up at that rate between two plates with a voltage of 800 volts. Okay, so what we're going to have to do is notice a few things. Okay, so if it's accelerating up, okay, that means that your F net equals ma. Well, it's going to be your force electric minus your force of gravity. Okay, and it will be moving up. Like, that means that the force electric has to be bigger than the force of gravity for it to be moving up, accelerating up, I should say. So we're just going to rearrange this. What are we looking for? The magnitude of the charge. We're going to rearrange this. We're going to substitute a few things in. So Fe is going to be from this formula here. So that's QE. And then Fg is mg. Now we're looking for that Q, so we're going to rearrange a little bit. Ma plus mg equals QE. So far so good. Now we're going to move the E over, so Ma plus mg over E equals Q. But that E is from this. It's the electric field strength. So now we're going to look at this to replace that E value. Okay, so Ma, let's maybe just take another step. Q equals Ma plus mg over V divided by D, I believe it is. Yes, indeed. Okay, so that's the denominator. We can move the D on top, so Q equals, and we can also take the M out of the brackets, GCF out the M. And so now we have this this formula here, and now we can go ahead and plug it in our calculator and solve it. I forgot to add the distance. Okay, so we needed that last little piece of information, but otherwise the rest of it should be correct. So 4.4 centimeters, 0.044 times by the mass, which is 9.1 times 10 to the exponent negative 14, sorry. Bracket 1.3, I think it was. Yeah, 1.3 plus 9.81 bracket divided by the voltage, which was 800 volts. And so we get 5.56 times 10 to the negative 17. And this is coulombs. Now it says find the number of extra electrons on the previous particle. So if that's what the charge was, essentially extra electrons is asking how many electrons does it take to make up that charge. So all we're going to do is take 5.56 times 10 to the negative 17 coulombs, and we're going to divide it by what one electron would be, 1.60 times 10 to the negative 19, and we're going to get our answer. So 1.6 times 10 to the negative 19, and we get 348. Yes, so let's just double check. Sig digs wise, we should have 2 sig digs, it looks like. So 347.5, I think is what we had. Yeah, 5.3. So we're going to round that to 3.5 times 10 to the 2 electrons. This is coulombs per electron, by the way, because it's an elementary charge. All right, let's continue. One more example. I recommend you press pause at this point and then try the question out for yourself. A small mass of 2.35 times 10 to the negative 4 kilograms accelerates from rest across an electric field for this distance. Given that it reaches a speed of that after the distance, what was the average force applied by the field over that distance? Okay, so what's happening here? There's a few things happening, but I think this is an interesting thing to think about. Work equals force times distance. Work also is your change in energy, right? So if it's changing energy going from rest, that's like EKI of 0, and then its final energy is going to be given by a half mv squared, right? The change in energy is our work. Work is force times distance. So all we have to do is then make a little bit of an adjustment here to say that this divided by distance is our force. And in this question, we always do final minus initial. But in this question, initial is 0. So it's basically just EKF over D is our force. So that's a half mvf squared over D. So F equals, and we're going to have another one, so a half m, which was 2.35 times 10 to the, whoops, that'll be wrong, times 10 to the exponent negative 4, times v, which is 3.4 times 10 to the exponent 2, but it's v squared, so actually like that, and then divided by the distance, which was 34 centimeters, so 0.34. And so it says we have 39.95 newtons as our average force. So given that we have 2 sig digs, it should be 40 newtons of force applied over that distance. All right, I hope this video helps you better understand both Millikan's oil drop and finding different values for charged oil droplets within a field. I hope it helps, and good luck.